All right, we are back. My name is Hong. I'm a software engineer at Facebook. I will be hosting the live Q&A today. We have today our guest, Nathan Satadru. Unfortunately, Yuan Mei, our third speaker, is currently in Beijing. The time zone difference makes it impossible for her to join us. So first of all, thanks to the speakers, Satadru and Nathan and Yuan, for their great talks. So Nathan, you mentioned that in a talk you were in Philadelphia. Are you still there, or you are back to the West Coast now?
I'm actually still in Philadelphia. Family business. So.
Cool. But you are based in Seattle, if I'm not mistaken.
Yes, I'm based in Seattle.
Okay. And Satadru, you are based in Bay Area, is that right?
Yeah, that's correct.
Okay, sounds good. Okay, let's get the Q&A session started. So we're going to have questions from both the emails and live streams. And I do see almost 90 audiences watching the video, so feel free to submit questions through the Q&A tab on the BlueJean app. We're going to monitor your questions and ask our speakers. So it's very interesting when I listen to both Tectonic and ArcDB, particularly ArcDB is built on Pangu. I saw there are a lot of similarities between these two systems. Both are using a pen-only storage backend, and also both utilize the key value store as the metadata management. So I have a question for both of you guys. First, the question is for Satadru. So the question is this. I wonder if the key value store used by Tectonic for namespace management is also built on top of Tectonic, just like ArcDB does.
Yeah, the answer is that today the key value store which we use on ZPDB is not built on Tectonic. It uses Paxos on a set of individual nodes, and that's why we don't have that recursion. But if you look at the literature, there are a couple of ways to solve this problem. Like, for example, a lot of the large-scale industry, it solves it by bootstrapping bigger clusters from smaller clusters. So that may be one way to solve this problem, but today we do not have that problem.
Okay, cool, thank you. Similar question. So you did mention that ArcDB is used as the metadata management for various cloud services like object storage, table storage, etc. But on the other hand, you didn't mention whether ArcDB is used for the namespace management for Pangu. Just curiously, are you planning on doing that, or is that already done?
So in ArcDB, actually, the design has an abstraction of the underlying file system where the only thing we're looking for is just a stream that consists of extend, because that's the data position we are talking about. So with this, it's okay to run ArcDB on a local file system. That's what we do, like in our experiments. We show in the first two experiments we show in the graph. But it's also possible to just move this thing to run on today's Pangu. So you can see that there's like for two different views. One is yes, you can of course use ArcDB for Pangu's master for metadata management. You can either use ArcDB on local file systems and build a Raft cluster, or you can just use ArcDB on a small, like very dedicated Pangu 1 cluster to support the Pangu 2's metadata management. With the Pangu implementation, then you can use ArcDB on top of that to provide the namespace, the metadata management for other services such as object store or like NoSQL.
Got it. I will put you on spot here. So just a follow-up. would you want to take a position whether it makes sense for ArcDB to be the metadata management layer for Pangu or not necessarily? Because I do know the previous version of the Pangu do use something very similar to HDFS name node.
Yeah, I would say it's unmuted. Okay, so yeah, I think it makes sense. We are actually in the talk with the Pangu team to see with the Pangu 2, the new design, they are actually looking for a key value store to manage their metadata. So we are actually in talk with Pangu team to do that. So I think, yeah, it makes sense.
Cool. I want to take a question from the live stream. This question is for Satadru. So the question is this: what is the concurrency strategy when two clients want to append to the same file?
Yeah, that's a great question. Basically, in Tectonic, what we provide is a single writer semantics for every file. So each of the files, when you open the file for write, that writer will have the exclusive access for appending to that file. So when you open the file, you can think about it that we can take a lock on that file for the write, and only that object will have exclusive write access. When another object if another process opens the file, so the second process gets the write access and the first process loses the write access.
Got it. Thank you. My next question is for Nathan. So the question is this: from the talk, it seems like ArcDB is optimized for new hardware architectures like NVMe devices, very fast data center networks. But I also assume that Pangu will also use high density mechanical disks for storage services like blob storage or data warehouses. How does Pangu manage such a heterogeneous storage infrastructure?
So I'm not definitely not an expert in Pangu because I work in a key value store. But as long as I know, the Pangu, especially the current version, the new version supports storage pools, which is based on the underlying device types. For example, there could be data written to the NVMe devices first because of the performance. Then during the compaction or garbage collection, we can naturally move the data based on either the capacity or the access patterns to slower media. But this only applies to the data, to the user data, for example, the blob data, where ArcDB is designed to maintain only the service metadata. So we would like those data to be kept on NVMe devices.
Okay, got it. Just a quick follow-up. Say, for example, for the case of, say, object storages, what's the typical ratio between the volume of the metadata and the actual user data, the blob storages? Like 1 to 1,000 or 1 to 10,000 ratios, just to have an idea, the amount of flash storage we may need to hold those metadata.
Yeah, that ratio will be much higher, but that depends on which cluster you're talking about. Because, for example, the object storage, they could be just pictures or movies. That will have a much higher ratio. But for file storage, if as long as I know, there are some customers, they just store very small files, like 100 bytes or 500 bytes, then that ratio will be much lower. So that really depends on which case we're talking about.
Okay, got it. My next question is for Satadru. So given that there's so many file system or even storage system available, why Facebook decided to create a new file system?
Yeah, that's a great question. So in the talk, I briefly covered actually that what was our previous generation storage systems and why with growing scale they become it was difficult to manage 3 different systems. Okay, so that was one of the reasons. And another reason is that like a lot of the other systems, like if you look at our paper, we covered that what are the differences with the other systems in literature, compare, like if we compare tectonic with the other systems, what are the differences? In couple of cases, it is always comes from the requirements and the scale, particular scale and the design requirements which we have. One example I can give is there are a couple of open source file systems where the metadata is managed by, there is no exact real metadata, but it is managed by a hash. Like if you just take the hash of the ID and then you store that in a node. With those kind of architectures, sometimes the problem happens is that you lose the flexibility of data migration when you want to control the migration speed. So that sometimes becomes a bottleneck. So this is just one example, but like most, like on a very very high level answer is that it kind of the scalability requirements and our workload specific requirements that makes that is behind the decision.
Got it. You touched. I want to have a follow-up question with Satadru. So you touched a base about the migration rollout, and you have in the talk you talked quite extensively on the migration rollout aspect. I think it's really important. Do you mind to share a little bit more? What are the hardest things to get it right in the rollout?
Yeah, sure. Yeah, so like yeah, as I mentioned in the talk, that basically like ensuring that your next generation storage systems performance is basically matching the previous generation, especially when you have different special systems for each of the different workloads, matching each of the performance, that becomes a tricky part, and that I covered in the paper and also in the talk. But there is another aspect which is also the fault tolerance part, that with the large scale, the fault tolerance like fault tolerance at scale, it becomes pretty tricky. One example is that we store most of our data in Reed-Solomon encoded way. Now, in a Reed-Solomon encoded way, there is one particular, like if one node is unavailable, so you distribute the read, or there is a fan out of the reads. Okay, so sometimes the fan out is 10x, or like depending on your RS encoding. Now, if you're sometimes it happens is that in our clusters, that if a large portion of your storage nodes is not available, so then you increase this reconstruction load on the rest of the clusters. So it overloads the rest of the storage nodes, and then it creates a cascading failure, because the overloaded nodes will reject the request, and then you will again go back to reconstructing the data, right? So it basically creates a cascading mode of failure. So handling those failure modes like is also very important. And in a new systems, like at the start of the system, you sometimes do not know all the failure modes. Actually, it is like when you run the system for a long amount of time, you know those kind of edge case failure modes, or like very tricky failure modes. So that's another area where basically the more you run the system, you know that yeah, these are the possible failure modes and how to solve those problems.
Great, thank you. My next question is from the live stream. This is for Nathan. So the question is this: what is the threshold for loss of data during failover for Alibaba Cloud?
I'm not quite sure like about what is the threshold for loss of data, but I can explain how the failover works. So basically, when there's a failure, we need to restart that single node. On the cloud, one single node usually supports like multiple runs multiple partitions. We call you can consider that as like a data, the shard of data. So when that happened, when the partition reloads, first like replace everything in the transaction log, which is used to recover the memory buffer. Those like that not persist to the file table, the backend storage. But for those data that has already been checkpointed, there's really like no need to do any recovery, because they're already on the persistent storage, and the only thing we need to do is to get the metadata, which is also actually replayed from the log, and get those root positions and the mapping table like data recover, like just sorry, not replayed, but just put in the memory, then we have the whole state recovered. So there might be like you're wondering is when there's a transaction running, there is a system failure. What happened to this transaction? So if the transaction is not finished, is not completed yet, then there's no commit record. So this transaction will be considered as a failed transaction. But if the transaction already like succeeded, but like doesn't have a chance to like send like a message to the client, in this case, from the client side view, they're gonna hit like a timeout error where they need to retry. Sorry, not retry, but do a query, do a get operation to see whether this transaction succeeded or not. Then they know like whether they need to retry or not. So this is how we deal with the failover.
Got it. Yeah, so this question probably is a little bit ambiguous. Let me try to poke a little bit. I guess what you're saying is that in general, any accepted requests, any acknowledged successful request, there would be no data loss and should be guaranteed to be persisted on the storage in the case of failover. Maybe maybe what this question is asking is any situation, for example, typically if it's a 3D copy replica, that means that if you really have a very simultaneous failure of 3 storage devices, then you would lose that data. I don't know if that's what the question is alluded to. Would you be able to elaborate, or maybe that's more towards the Pangu side you may not be very familiar with?
Yeah, so from the key value store, like basically the middle layer, when we talk to Pangu, I think the assumption is whenever we get the result from Pangu saying it's succeeded, then we assume it's there and won't be lost. There will be cases like for replicas all like gone, of course, but other than that, we consider the data is persisted. Then when we acknowledge the user request saying this transaction succeeded, there's no like a threshold. We just guarantee that transaction succeeded and the data is there, so it's not lost.
Okay, great. So let me move on to Satadru. So I think in your talk you mentioned that Tectonic is data center scale. So why do you stop at the data center scale? Why not just make it a global scale storage system?
Yeah, so we felt that building Tectonic is the basically storage building block of storage, and on top of Tectonic you can build a global storage which is like data center fault tolerant. So providing a basic storage layer, building block of storage layer which scales within the data center, that seemed like a very simple building block. On top of the building block you can build a global storage. The reason within a data center makes sense is that within a data center you have enough, especially in our data center network architecture, fabric based. So you have enough node to node, cross node network bandwidth, and also you have a very predictable latency. Whereas if you go across the network, you need a different type of optimizations because you have an unpredictable node to node latency. Like for example, if your data center 1 and data center 2 is located very farther apart, it will like the latency is proportional to the distance between the data centers, right? So it adds a separate layer of like in variable latency. Okay, so that's why we feel that if we separate out these two layers, we obviously support a lot of global storage solutions on top of Tectonic, but which are like outside, like on top of, it is built on top of Tectonic. They are specialized to solve those problems. Actually, how do you solve the variable latency problem? How do you solve the data movement between the two different data centers? How do you make sure that you have enough backbone network capacity and etc. those problems. Whereas within data center, we try to solve the simpler problem of like providing a durable storage and act as a building block for the upper level storage systems.
I want to piggyback on Satadru's answer about this global scale storage. Just curiously, for Nathan, what is Pango's approach to support global storage availability? Anything similar or different from Tectonic's approach?
I think I'm going to give you like a quite a similar answer. So I think first, yes, due to the like latency or like some other considerations, I think each Pango file system is also designed to be available in a single availability zone. Then on top of this, like services such as like the object store, they can use like multiple Pango file systems to achieve like the cross AZ availability. So it's quite similar, I would say.
Great. I have not follow-up, another question for Nathan. Just curiously, so B-tree or its variations are well studied in the literature, decades of studies. And my takeaway from ArcDB is that you're trying to optimize many things, right? Amplification, consistent read and write, consistent read and write performances, high concurrency, snapshot isolation consistency, fast recovery, fast split and merge. It seems like you can do everything. So it's just curious question. And normally in a system study, researchers will always say that there's always a trade-off. You get something, you give up something. There's no floating world. So is there anything that ArcDB does not do very well compared to maybe other key value stores? In other words, what kind of trade-offs are you taking in designing ArcDB?
No, there is no trade-off. Of course, I was kidding. So, first I would say it's a complexity. Like it's either design or implementation. You can see the architecture we show. You can actually like you can consider the original paper from Microsoft talking about the BW tree. It was already complicated, talking about like how to implement the latch-free in-memory mapping table operations. Now, coming days, we have to maintain this mapping table, but dealing with the persistent storage. So things are quite complicated, like dealing with the checkpoints and compactions. And we need to have like whole new compaction policies instead of using the well-studied leveled compaction. So things like this are quite complicated. The second, I think, is a very big one is we have to rely on the random read like performance, because we maintain like so many small delta pages that append to the base pages. Those are like very small pages, and whenever we do a compaction, we need to read those pages out, then merge with the base page and write into new pages. So those are just random read. They're different from the LSAM tree where you just read a big chunk of a SS table. So this makes it like the ArcDB, like I would say, not suited for the slower like HDD and network. So I think that's the biggest trade-off.
Thank you. So you mentioned the complexity. So it does sound very complex to me. So how do you ensure your implementation is correct? Particularly, there's all kind of consistencies, researchers you get involved. How do you curb the complexity, making sure your implementation is actually bug-free, or even your protocol is designed properly?
Yeah, it's quite complex. Like even our today's implementation is a little bit like complicated. But we took like two roads. First one is we have several trade-offs during our design, just to simplify the testing and the reasoning. For example, like the page mapping table operations. When we first think about how to maintain this, so we try to achieve like completely concurrent checkpoints and compactions. Then we realize it's like a little bit too difficult, and especially for reasoning. So although they can happen like concurrently, when they commit, today's design like required them to happen to commit in order, or like based on their timestamps. So this will limit the conflicting cases. Like because like they commit in order, so we know there could be like only this many cases. So this is the first approach. Like we just make trade-offs on performance and sometimes write amplifications just to simplify the cases. And the second one is I'm not an expert on this one, but I know like there are some verification techniques. For example, like we are doing formal verification. Some people is helping us to do this just to ensure the correctness.
Great, thank you. Thanks for the answers. And I want to ask a similar question to Satadru. Basically, again, put you on the spot here. So, in what aspects of a tectonic you may consider not as good as some other systems? In other words, what kind of trade-off you deliberately make in tectonic?
Yeah, that's a very valid point actually. So yeah, so if you look at our there are actually quite a lot of things actually where we can compare, and there are some trade-offs. So one aspect is the disaggregated metadata architecture. So the way the thing which I mentioned in the talk also, that we split the directory to list of files, file to list of blocks, and blocks to list of chunks into 3 different metadata layers, so that each of the layers can scale independently. But one like disadvantage of this is that you have you have more round trips to get for example, if you want to open a file, during opening the file you'll have to get the directory information, then list of block information, and then list of chunk information. So as a result, basically sometimes the metadata for a couple of operations, the metadata latency is higher compared to our previous, let's say if you compare with HDFS, where you have a single name node and you just go there and you do all the in-memory operation and then send back the data, which is just one round trip. So that way, actually, in a couple of cases, the metadata operations are expensive. So another point which is also related to the metadata, because we have these disaggregated metadata layers, so we do not provide the key value store, which is single. It provides a transaction within a shard, not a cross shard transaction. So whenever you have a cross shard transaction, or you need, for example, you want to move a directory move a file from one directory to another directory, so it is 2 different shards, right? So there actually, if you want to provide consistency guarantees, so that becomes hard.
Got it. I have a kind of follow-up question for Satadru on this regard. So if I comparing the 2 talks, you mentioned the 2 use cases. One is object storage, the other is data warehouse, mainly append only. Nathan, in ArcDB, we have 3 use cases. One is obviously the common object storage use case. The other 2, which is table storage and file storage, that seem to have some kind of read-write patterns in the data, not in the metadata. Just curiously, is that a design choice you guys intentionally make for Tectonic, mainly focusing on storage, that the user data is also can be supported by can easily supported by append?
Yeah, so so Tectonic basically acts as a building block of storage for most of our storage use cases. So as we described in the talk, that like for a couple of our large storage use cases, we do not need any in-place updates, or like append only is good enough. Okay, and another point is that the append only semantics definitely simplifies your, like, as the lowest level of storage, you want to keep the design very simple. Append only definitely helps you keep the design very simple, because most of the one example is that within a file, most of your blocks are already sealed. That means that the block size, checksum, they are not changing. The whole block metadata is not changing. You can cache that data without worrying about consistency. So those kind of simplifications are possible with the append only design. And then the final point is that if you want to build a in-place write semantics, you can build it on top of append only semantics by using a journal, and then implementing some sort of compaction. Obviously, that implementation has complexity, but like you put the complexity into the localized, or like whoever is using that, they can build that kind of a semantics there.
Great, thank you. Great. I want to turn to Nathan. So I didn't fully get your comparison between RocksDB and ArcDB, data ingestion experiment. Just curious, is the comparison fair? You mentioned that there is ArcDB uses, if I don't mistaken, use user level threads. Maybe RocksDB use kernel level threads, and also why are we only comparing the ingestion speed, and why don't we also compare the query performance after the ingestion?
Yeah, so it's not a direct comparison because yeah, as you mentioned, yes, ArcDB uses actually coroutines. That's supported by our authority model, and then RocksDB, based on like what we can find today, like the open source one, it only supports the actual threads, the kernel threads. So I would say when the thread count reaches a certain number, there will be like lots of time spent on the context switch. So we just increase the thread count for RocksDB to reach that point, which we have this maximum throughput. Is I would say is like fair. We can of course like modify RocksDB to use like either async threading model or like just use coroutine. That's a lot of work, and that involves lots of implementation details. If we have a bad implementation, for example, it's gonna still like tank the numbers. So our focus instead is just to reduce the write modification and like reduce the performance fluctuation from the compaction or garbage collection traffic. So we just think like there's no need to do that. Like it's just not our focus.
Got it. Just quick follow-up on one aspect. My understanding is if you're using coroutines, you may not be able to using multiple processors. Are you saying in that experiment, one processor's performance beats the multi-processor performance on the RocksDB?
Oh no. We still use multiple threads. It's just when I say coroutines, it's just in one thread. It can still does multiple things together, like execute multiple transactions together. When one transaction, for example, does an I/O or with for some kind of like a lock, it can just yield to another coroutine. But in general, we have like multiple threads running.
Okay, got it. What about the second part of my question? So, have you checked the query? Yes. Yeah.
Yes. It's just there are like lots of numbers we're not included in this presentation, but in the paper there are numbers for the query performance and the read performance.
Terrific. Thank you. I sure will read the paper. So looks like we're coming down to the last question, which is also coming from the live stream. This is for Satadru. So the question is this: does this unify the cluster auto scale? And the related question is, how does the repartition data when nodes are added removed?
Okay, so yeah, here actually the probably the answer depends on what you mean by auto scale, but I will try to explain actually like let's say if you just think about, let's split the problem into two parts. So one part is the data part and one is the metadata part. Okay, so in the data part there is nothing to repartition as such, but if you add, let's say, new node to your cluster, so some of the nodes will be empty and some of the nodes will be full, right? So the background rebalancer process will eventually move the chunks into the and try to make sure that each of the nodes are almost evenly full, and it will update the metadata. So that kind of handles the how you can add more storage nodes and how you can expand the cluster. Okay. The other part is actually the metadata part, which I think the repartition question comes from, actually, if I understand correctly. In the metadata case, like what we have, our unit is one shards, but you can host multiple shards in one host. So you can change the number of shards. Like for example, if one shard gets very hot, then you can, in that host, you can host less number of shards. So you can still change the number of metadata nodes, and you can redistribute the shards without change, or like while you are serving the live traffic.
Great, thank you. I think that's all the questions we have for today. So this wraps up this week's Ask Your System at Scale conference. Just a reminder, we have one more week left, so feel free to tune in. And thanks to our speakers, Satadru and Nathan. Hope you guys hope everybody has a great day, and hopefully we can meet again next week.
Thanks, Sam.
Yeah, thank you.